Hello everyone, welcome to this lecture. So, now in this lecture we will continue our discussion regarding domain extension for perfectly secure broadcast, and we will first see a warm up protocol. This will not be the exact domain extension protocol and this will be inefficient as well, but later on we will see how this warm up protocol is used in the domain extension protocol. Okay, so, in this warm up protocol, for simplicity we will assume n is equal to exactly 3t plus 1. So, remember that for perfectly secure broadcast and Byzantine agreement, and the condition n greater than 3t is necessary and sufficient. So, n equal to 3t plus 1 is the minimum value of n for any given t satisfying the condition n greater than 3t. The reason we are making this assumption n equal to 3t plus 1 is that it helps us during the analysis of the communication complexity, because we can then use the fact that asymptotically t is equal to theta of n. So, I am assuming here that all of you are familiar with big O, omega and theta notations. They are asymptotic notations. And if you are not familiar with them, please refer to any standard text on data structures and algorithms. Also, in this warm up protocol, we will assume that all the operations are performed over a finite field f, where the only restriction on the field is that its size should be at least n plus 1. Now, in this warm up protocol, the sender will have a message m, which will be of size t plus 1 times log of cardinality of f bits. Okay. And it will be a broadcast protocol. So, this is a broadcast protocol. Where the goal of the sender will be to send its message identically to all the parties, and that should happen even if the sender is potentially corrupt. And the overall communication complexity of the warm up protocol will turn out to be this much. So, n square log of field size communication will happen over the pairwise channels among the parties, and apart from that the protocol will also incur a communication will also incur a broadcast of n square bits, and that broadcast can be instantiated using any existing bit broadcast protocols. Okay. So, that means there are two parts of the communication complexity in this warm up protocol, whatever communication happens over the point to point channels and whatever communication should happen by invoking instances of bit broadcast. So, the communication which should happen through instances of bit broadcast, that will be of order n square. Okay. So, there will be several phases in the protocol. The first phase will be a sender dependent phase, which will depend completely upon the sender, because sender will have to send these messages. So, remember recall that sender's input is a message consisting of t plus 1 times log of field size bits. So, what the sender does is the following: it divides its message into several blocks of log of field size bits, and each such block of log of field size bits can be interpreted as an element of the field, because each element of the field can be represented by log of field size bits. So, whatever is the first chunk of log of field size bits, that is converted into a field element, let us denote it by m sub 1. In the same way, next block of log of field size bits of this message m will be interpreted as a field element, we denote it by m sub 2, and like that the last chunk of log of field size bits of the message small m will be mapped to the field element m sub t plus 1. This is what sender is doing. Now, the goal of the sender is to send this message identically to everyone. So, if we would have been in the semi honest setting where all the parties including the sender also would have followed the protocol instructions correctly, then sender could have simply sent this message over the point to point channel to every other party. By the way, we are assuming here that there is a pairwise secure channel between every pair of parties, namely we are in the secure channel model. So, if it would have been guaranteed that sender will not misbehave, then the simple way of broadcasting sender's message will be to ask the sender to send its message individually to the first party, individually to the second party, individually to the nth party. That would have required a communication complexity of order of n times whatever is the size of the message, but it is not guaranteed that sender is honest. Sender could misbehave. It can send different m to P1 and a different m to P2 and so on. So, that is why to send its message, what the sender does first here is the following: it computes a Reed-Solomon code word corresponding to its message. So, notice that even though the sender's message is a bit string, it can be mapped into a message consisting of T field elements, and then we can compute a Reed-Solomon code word corresponding to that message. Namely, the sender will form a message encoding polynomial whose degree will be T, and there will be n publicly known evaluation points alpha 1, alpha 2, alpha I, alpha n, and that message encoding polynomial will be evaluated at alpha 1, alpha 2, alpha I, alpha n to get the corresponding Reed-Solomon code word whose components are C sub 1, C sub 2, C sub I, C sub n. Now, to send the message m, sender sends this full code word vector to every party. So, to the first party it sends the code word, to the second party it sends the code word, to the ith party it sends the code word, to the nth party it sends the code word. Now, if sender is honest, it would have sent the same code word copied to every other party, but it is not guaranteed. We do not know whether sender is honest or not. So, that is why the code word copy which P1 receives, there I am using two level of indices. So, P1's code word will be denoted by C sub 1 1, C sub 1 2, C sub 1 n. So, the second level of indexing denotes the code word component, and the first level of indexing denotes the copy of the sender's code word as received by P1. In the same way, I am using a two level indexing for the copy of the code word which P2 has received, a two level indexing for the copy of the code word which Pi has received, and a two level indexing for the code word copy which Pn has received from the sender. How much communication this will require? Well, to send the code word to one party, it will require a communication of order of n times the log of field size bits, because the code word consists of n field elements and each field element is represented by log of field size bits, and since sender is sending the code word to every party, the overall cost will be n times the cost of sending the code word to one party, and that is why the cost of this phase will be order of n square times log of field size bits. Notice that no broadcast has happened as of now. That means no invocation of bit broadcast has happened, to be more specific, because this communication is happening over only the point to point channels. Now, once sender has communicated its copy of the code word to the respective party, the rest of the protocol will do the following. In the rest of the protocol, the parties will interact and they will try to verify whether sender is behaving honestly and whether sender has distributed a common code word to sufficiently many parties. Ideally, this should be the case if sender is honest, because sender should have sent the same common code word to all the parties, but as I said, if the sender is Byzantine corrupted, it may not do so. So, that is why now the parties have to interact and verify whether the sender has distributed a common code word to sufficiently many parties. I stress sufficiently many parties and not all parties, because we can never verify whether the sender has given the same code word to all the parties, because if say Pn is corrupt, it may simply say that I have received a junk from the sender. It can simply say, it can simply produce a junk copy of the code word claiming that it has received from the sender even though sender has not sent it. And in that case we can't trust whether the sender has indeed cheated Pn by sending a junk code word or whether it is Pn who is reporting incorrectly against the sender. So, that is why we can only guarantee here that all the honest parties can verify whether they have received the same common code word or not. So, that is why this sufficiently right now is in quote unquote, but basically we will try to ensure that sufficiently many honest parties confirm whether they have received the common code word from the sender or not. And if it is guaranteed that sender has distributed a common code word to sufficiently many honest parties, then the next goal will be to ensure that all honest parties apart from those sufficiently many parties also obtain that common code word. If that is ensured, then it will be now guaranteed that in the system all honest parties have a common code word received from the sender, and the message corresponding to that code word will be the overall output for the warm up protocol. Now, for this rest of the protocol part where the parties need to do the verification and then they need to do the transfer of the common code word, the allowed communication budget for us is this much, namely the total communication of the over the point to point channels should be n square times log of field size, and if at all we are invoking any instance of the bit broadcast, there can be at most order of n square such instances. That is what is allowed, because that is what we require from this warm up protocol when we plug it later in the domain extension protocol. So, now let us see how the verification proceeds. So, this will be now a sender independent phase, and this happens once the sender has distributed the code words to the respective parties. So, let us see what is the interaction happen, or what kind of interaction happen during the verification process. So, recall that party Pi has its own version of the local code word as received from the sender, and every other party has its own version of the local code word. One simple way of verifying whether sender has given the common code word to sufficiently many parties is that ask every party to broadcast their received common code word by invoking instances of the bit broadcast. That will be simply requiring an enormous amount of communication that will not satisfy our allowed budget. So, we have to do the verification in a very communication saving way. So, to do the verification, every pair of parties exchange only two supposedly common components of their respective code words. So, for instance, if sender would have been honest, then we expect that the first component of the ith party's code word and the first component of the first party's code word should be identical, and the ith component of the ith party's code word should be same as the ith component of the first party's code word. So, that is what party Pi tries to verify. So, party Pi sends only two common components, it is not sending the full vector, full code word vector to P1 and asking P1 to check whether the code word which Pi has received from sender is same as the code word which P1 has received from the sender. No, they are only trying to verify the commonality of two supposedly common components. In the same way with the second party, Pi exchanges only the second component of its code word and the ith component of its code word. With the jth party, it exchanges the jth component of its code word and the ith component of its own code word, and with the nth party, it exchanges the nth component of its code word and the ith component of its code word. How much communication this phase will require? This will require a total communication of order of n square log of field size bits, because for one party only this will require order of n times log of field size bits of communication, but this pairwise exchange happens for every pi. So, I have demonstrated it only for one pi, but this pairwise exchange of two supposedly common point is happening for every party. So, P 1 would have been exchanging two common components with P 1, P 2, Pi, Pn. P 2 also would have been exchanging two common components on its received code word with every other party, and like that Pi is anyhow exchanging two common components of its received code word with every other party, and like that Pn also would have been exchanging two common components on its received code word with every other party. So, it is order n for one, order n field elements for one party, order of n field elements for the second party, order of n field elements for the ith party, and order of n field elements for the nth party. So, that is why total it will be order of n square field elements of communication, and each field element is represented by log of field size number of bits. So, that is why this phase will incur a communication complexity of this much, these many bits. So, we have not crossed our allowed budget. That means, till now the sender dependent phase communication complexity was n square field elements, and so is the communication complexity for this phase as well. Until now no instance of bit broadcast has been invoked. Now, based on the pairwise consistency test which happens here, every party will now publicly declare the result, whether the test is positive or negative. So, what does that mean? So, recall that till now the following has happened: sender had a message and it computed a Reed Solomon code word for that message. A copy of that code word was sent to the ith party, and a copy of that code word would have been sent to the jth party for all pi pj in the system. And then after that pi would have sent two common values, two supposedly common values on its copy of the received code word to pj, and pj also would have sent two supposedly common value on its received code word to pi. Ideally, if sender pi and pj are honest, then component wise Cii should have been same as Cji, and Cij should have been same as Cjj, and yeah. So, that is what should have happened. Okay. If both if sender pi and pj are all honest, but we do not know whether sender pi and pj are all honest or not, they may or may not be. Okay. So, now what every party does is the following: it prepares a Boolean response vector based on the values which it receives from the other parties, and pj also will prepare a Boolean response vector. Now, if we consider the ith party's Boolean vector, the jth component of that vector determines whether pairwise consistency of pi's and pj's code word is positive or negative. Namely, pi will say that okay, I am fine with pj, which is equivalent to saying that I mark pj as 1, namely my response for j is 1 only if the Cji component received from pj matches my own ith component, and the Cjj component received from pj matches my jth component, which should ideally hold if sender Pi and Pj are all honest. But if either this condition is not satisfied or this condition is not satisfied, then Pi will conclude that it is either the sender who is faulty and has sent different code words to me and Pj, or it is Pj who is corrupt and he is unnecessarily exchanging incorrect components with me, due to which the checking fails. But Pi can't conclude whether it is the sender who is corrupt or whether it is a Pj who is corrupt. He will simply accuse Pj that okay, no, I am not satisfying, I am not matching with j. So, that is my response for j is 0. So, that is the way Pi would have prepared the Boolean response vector. So, Pi would have received 2 values from P1, from P2 it would have received 2 values, from Pj it would have received 2 values, and from Pn it would have received 2 values. The pair of values received from P1 is compared by Py, and if the pairwise consistency is satisfied, then he will mark P1 to be ok, otherwise he will mark P1 to be not ok. In the same way, the pair of values received from P2 is verified by Pi against its own code word, and accordingly P2 is marked as 1 or P2 is marked as 0, and so on. In the same way, party Pj, it is also receiving a pair of values from Pi, and the way it marks its ith entry, namely the way it labels the ith party, is as follows. It checks whether these two conditions are satisfied. If they are satisfied, then he says that I am okay with 1, otherwise he will say I am not okay with I. It will say I am okay with I, otherwise it will say I am not okay with I. Okay. And like that, Pj would have filled each of the response vector bits. Okay. Now, once every party has prepared its Boolean response vector, it makes it public, and when I say it makes it public, to do that it invokes an instance of existing bit broadcast protocol. Okay. So, now Pi acts as a sender, where the sender's input is this Boolean vector, it invokes instances of any bit broadcast protocol, say the king face protocol, to broadcast the first bit in its response vector, the second bit in its response vector, the ith bit in its response vector, the jth bit in its response vector, and the nth bit in its response vector. So, namely n instances of bit broadcast. So that all the parties receive an identical copy of ith party's Boolean vector. In the same way, Pj also will invoke instances of any existing bit broadcast protocol by acting as a sender to broadcast the individual bits in his response vector. Now, see here, if Pi, for instance, if it is corrupt, then instead of he can first of all fill its Boolean vector arbitrarily. That means, even if the Boolean vector entries should be 1, it can simply say it is 0. That means, it may simply unnecessarily accuse Pj, or it may simply broadcast a garbage Boolean vector which has no meaning at all. So, we can't ensure that whether every party is broadcasting its genuine Boolean vector, but what we know is that if Pi is honest, then it will indeed fill its Boolean vector as per this assigned process, and indeed it will broadcast its Boolean vector correctly. So, honest parties, they are guaranteed to compute their Boolean vectors as per the protocol steps, and they are guaranteed to broadcast the genuine Boolean vector. Okay. And as I said earlier, if the sender is honest, party Pi is honest, and party Pj is honest, then the jth component in ith party's Boolean vector and the ith component in the jth party's Boolean vector should be 1. That means, they should be mutually okay with each other. Okay. And this phase requires instances of any existing bit broadcast protocol. Specifically, there are n square instances of existing bit broadcast protocol, and that will amount to a total broadcast of n square bits, which is within our allowed budget of the warm up protocol. Now, after the parties make public their response vector, they will be known to everyone, and notice that till now the following communication has happened. So, parties have made their response vectors public, and each party has its own copy of the Reed Solomon code word received from the sender. Now, based on the publicly available response vectors, the parties will construct a graph which is called a consistency graph, and where the nodes of the graph will be the identity of the parties, namely P1, P2, Pi, Pj and Pn, and an edge will be added between the parties Pi and Pj if and only if the jth component in the ith party's response vector and the ith component in the jth party's response vector are 1. That means, the party Pi and Pj are mutually consistent with each other. So, if this condition is satisfied, we will say that the ith party and the jth party are pairwise consistent with each other, and this means that if Pi and Pj are honest, then component wise in the ith party's code word, the ith component is same as the ith component in the jth party's code word, and in the same way component wise the jth component in the jth party's code word is same as the jth component in the ith party's code word, because that is why party Pi and Pj would have broadcasted Vij equal to 1 and Vji equal to 1 if both of them are honest, because they would have verified that these two conditions are satisfied. Of course, if Pi and Pj are not honest, that means even if these conditions are not satisfied, it may happen that the corrupt party among Pi and Pj may unnecessarily say I am okay with the other party, that is fine. In that case we can't claim anything, but what we can claim is that if at all there is an edge between a pair of honest Pi Pj in the graph, that means component wise their code words, their respective local code words have the same two components, namely the ith component in their respective local code words are same, and the jth component in their respective local code words are also same. Okay. Now, parties check if there is a click, and when I say click, I mean to say a complete graph. They check if there is a click or a complete graph of size at least 2t plus 1 present in the consistency graph, and if they see that there is no such click present, then they discard the sender. When I say discard the sender, I mean to say stop the protocol at that point only, do not do anything else, and simply output a bit string consisting of t plus 1 times log of field size number of zeros as the overall output for the protocol. Okay. So, first of all, notice that this graph will be public. That means, all the parties will be constructing the same copy of the conflict graph. This is because the conflict graph is computed based on the response vectors which have been made public using invocations of the bit broadcast, and the bit broadcast would have ensured, its consistency property would have ensured that every honest party receives the same version of V1, same version of Vi, same version of the vector Vj, same version of the vector Vn. That means, if party 1 has added the edge Pi Pj in its copy of the consistency graph, and if P1 is honest, then it is guaranteed that every other honest party also would have added the same edge. Now, what is the logic behind discarding the sender here? If sender is honest, then all honest parties will be a part of a clique. In the graph G, because every honest party Pi will be consistent with every other honest party Pj, because an honest sender would have sent the same common code word to all the honest parties, even to in fact to every other party, but corrupt party might simply replace those code words with some other junk code word and might proceed in the protocol, but all the honest parties will stick to the version of the code word as sent by the honest sender. And when every pair of honest parties Pi and Pj would have exchanged the common components, they will see that their supposedly common components are indeed common, and that is why they would have marked the other party as 1 in their respective response vectors. So, if sender is honest, we expect that all honest parties are a part of a clique in the graph, and how many such honest parties are guaranteed? At least 2t plus 1, because we are working with the set in the setting where n is equal to 3t plus 1. So, at most t parties can be corrupt who may not be pairwise consistent with the honest parties, but there are at least 2t plus 1 honest parties who are guaranteed to be pairwise consistent, and they will be a part of the clique. So, for an honest sender, this step will not be executed because this condition will not be satisfied. That implies that if at all a clique of size 2t plus 1 is not found in the graph, that means the sender is definitely corrupt and it has not distributed the common code word, a common code word to all the honest parties. So, it is fine to simply stop the protocol, pretending the dealer to be corrupt and take some default output as its message. That means, we do not care what exactly was sender's message. Since you have not behaved honestly during the protocol execution, we will not participate further and we will treat as if you wanted to broadcast a message consisting of all zeros. That is the logic behind this step of discarding the dealer. However, it could be possible that a clique of size 2t plus 1 is obtained even if the sender is corrupt. Of course, for the honest sender, such a clique is guaranteed, but it could be possible that even a corrupt sender, sorry, not dealer, even a corrupt sender has sent the same common code word to sufficiently many honest parties and a clique of size 2t plus 1 is obtained. If a clique of size 2t plus 1 is obtained, let us call that subset of parties as core. Now, what we can conclude regarding core? Well, we can conclude that there are at least t plus 1 honest parties in core, even though its cardinality is 2t plus 1, t of those 2t plus 1 parties may be corrupt under adversary's control in the worst case, but even in that case there are at least t plus 1 honest parties in the core who are guaranteed to be honest, and those honest parties would have genuinely performed the verification pairwise consistency test and would have marked the other parties, other honest parties within the core as 1 in their respective response vectors. That means, the local code words of all honest parties, I stress only the honest parties in core, I am not saying all parties in core, that is I am stressing all honest parties in core have at least t plus 1 common components, because that is why they have constituted a clique in the graph, because whenever there is an edge between a pair of honest nodes in the consistency graph, that means they have common components, they have respective common components in their local Reed-Solomon code words. And how many such edges are there between pairs of honest parties? So, well, we are guaranteed that there is a clique involving at least t plus 1 honest parties. So, based on their response, we can conclude that there are t plus 1 honest parties in the core and their respective local code words have at least t plus 1 common components. Now, here we trigger one of the properties which we have discussed regarding Reed-Solomon code words in our earlier lecture, which says that if you have two code words which have t plus 1 or more common components corresponding to message encoding polynomials of degree t, then that implies that the two code words are actually the same code words. So, what is the message encoding polynomial? In this case, the message encoding polynomial, its degree is t, and we have come to the conclusion that the local code words of all honest parties in core have t plus 1 or more number of common components. That automatically implies that all honest parties in the core have received the same code word from the sender. Okay. So, that is the conclusion till now. That means we have ensured here, we are ensured here that if at all a core is obtained, then all the honest parties within the core have received the same code word from the sender. So, without loss of generality, imagine core consists of the first 2t plus 1 parties, but it could be any subset of 2t plus 1 parties, and it could be possible that there are some honest parties outside core whose local code word might be different from the common code word held by the honest parties in the core. So, that is why now to complete the protocol, what is left is to ensure that every party pi who is honest, irrespective of whether it is a part of the core or not, gets the same common code word which is guaranteed to be held by the honest parties in the core. Okay. So, we have honest parties who may be inside the core as well as outside the core. Inside the core, all the honest parties are guaranteed to have the same code word, but as I said, it could be possible that there are some honest parties outside core whose code words as received from the sender might be different from the common code words held by the honest parties inside the core. So, to get rid of this mismatch, we now have to ensure that even the honest parties outside the core gets the same common code word. In general, our now goal is to ensure that every honest pi, irrespective of whether it is inside the core or outside the core, gets the same common code word as held by the honest parties in core. Now, to do this, there are several ways, but remember that we want a mechanism where the allowed budget for communication complexity is this much. So, to respect this allowed budget, what every party pi will do is the following. Every party pi will simply ignore whatever code word or whatever the ith component of the code word it has received from the sender, because it does not know whether sender was honest or whether sender was corrupt. Party pi now knows that who are the parties in core, because it also would have obtained the same code by finding the click, and what it knows is that it is a parties in core who have the same common code word, specifically the honest parties. So, what it will do is it will try to redefine, or it will try to adapt the ith component of its code word to the ith component of the code words held by the honest parties in the core. Now, ith component of the code word held by the honest parties in core is guaranteed to be same, because all the honest parties in the core have the same common code word. So, how pi redefines its ith component? Well, remember that earlier every party would have sent two common values to pi as part of the pairwise consistency test, okay, all the n parties. Now, pi will go back to that round, and now it knows the identity of the parties in the core. It will only focus on the ith component as received from the parties in core. At that time, it would not know the size, it would not know the identity of the core, but now it knows the identity of the core. So, it simply ignores the ith component received from the other parties who are outside the core. It only focuses on the ith component received from the parties in the core, and now whatever Ci it has obtained earlier from the sender, it simply ignores it. So, remember, sender would have sent a code word to the party Pi and their ith component would have been there. Now, Pi simply goes and forget that Ci and changes its Ci to this value, namely it takes the majority of the ith component of the code words of the parties in core as received earlier. Now, what is the logic behind this redefining the ith component? Well, we now know that the majority of the parties in core, because the size of core is 2t plus 1. So, t plus 1 are honest and at most t could be corrupt, and since all the honest parties in core would have sent the same ith component because their respective code words are same, that will ensure that by redefining the Ci based on this majority rule, the redefined Ci that Pi will have is same as the ith component of the common code word held by the honest parties in core. Okay. So, this step does not require any communication, no communication, okay, because this is based on communication which has happened earlier, but that time the identity of the core was not known, but now the identity of the core is known. So, at this point each party will now have the common, each party will now have its respective component of the common code word held by the honest parties in the core. Okay. So, imagine that the common code word held by the honest parties in the core has the components C1, C2, Ci, Cn. Because of the redefining step that we have executed just now, P1 will be having the component C1, Pi will be having the component Ci, Pn will be having the component Cn, and Pj will be having the component Cj. Okay. But that does not complete the protocol. We now have to ensure that every party P1, P2, Pi, Pn has this full vector, namely the common code word held by the honest parties in the code, because that exactly is the code word which everyone would like to have, which sender has given only to the honest parties in the code. So, for this what we do is the following: every party send its redefined component to everyone else. So, P1 will send C1 to everyone, Pi will send Ci to everyone, Pj will send Cj to everyone, and Pn will send Cn to everyone. This will require a communication of n square field element. Of course, if Pi is corrupt, then it may change Ci to Ci prime, or it may send a garbage Ci to parties. So, what the parties can now do is the following. So, let us denote the vector of values that each party now have after this exchange as C1 prime, C2 prime, Cn prime. If Pi is honest, then Ci prime will be guaranteed to be same as Ci, but if Pi is corrupt, then Ci prime could be a garbage value. But what we now know is that we are working in the setting where n is greater than 3t, and C1, C2, Ci corresponds to a message encoding polynomial of t degree. Okay. Specifically, we are working in the case where n is equal to 3t plus 1. So, 3t plus 1 is the length of the code word, and what is the length of the message encoding polynomial? It has t plus 1 coefficients, and how many parties can send incorrect redefined components? Up to t. So, this condition is satisfied, that means whatever condition needs to be satisfied for Reed-Solomon error correction or error correcting T errors will be satisfied, and as a result every party after applying the Reed-Solomon decoding algorithm on the received vector of redefined components will be able to recover back the message corresponding to the common code word held by the honest parties in core, and this will require a communication of only n square bits, n square field elements. So, if we outline this warm up protocol, it has multiple stages. The first stage is the code distribution, where sender converts its message into a code word and sends the code word to everyone, and then the second stage is the pairwise consistency test, where every pair of parties exchange only a constant number of supposedly common points, and then they publicly announce the response vector. For this step, any existing bit broadcast protocol can be used. Based on the publicly available response vectors, the parties prepare a consistency graph, and then they check whether there exists a sufficiently large subset of parties, a core subset of parties of size 2 t plus 1, who are all pairwise consistent, guaranteeing that at least t plus 1 honest parties have received a common code word. If that is the case, then based on the communication the parties had in this pairwise consistency check phase from the parties in core, every party redefines the ith component of their individual code words. This does not require any communication, and once every party has their respected redefined component, the goal will be to obtain the common code word held by the parties in the core. For this, every party exchange the redefined component followed by Reed-Solomon error correction. This will require a communication of n square field elements. So, you can see most of the protocol only involves communication over point to point channels. The existing bit broadcast protocol instances is required only to make the response vector public. So, this is the reference used for the warm up protocol. In the next lecture, we will see how we can plug in this warm up protocol to get the actual domain extension protocol. Thank you.